So, welcome back to lectures on engineering mathematics 2, and this is lecture number 37 on half range Fourier expansions. So, in this lecture we will see the half range Fourier sine series expansion and also the half range Fourier cosine series expansion. So, in the last lecture we have already seen that the Fourier series for even and odd functions can be simplified. So, if f is an even function, then f x can be expressed in terms of just the cosine functions, and these coefficients a n can also be simplified, just they can be evaluated from the 0 to L and 2 times, because the originally it was minus L to L, and then we have this f x cos and pi x over L dx, and n is for 0, 1, 2, etc. So, because the function is even, we have observed that the b n coefficients become 0 and we got only the cosine series. Similarly, when f is an even function, we will get only the sine terms in the series, and the coefficient b n can be evaluated with the help of this simplified integral again 0 to L. So, we have again considered this 2 times the integral 0 to L f x sine n pi x over L dx, and n is again here 1, 2, etc. So, this was the simplified form depending on the function. If it is an even function, then we will get only the cosine terms, and if we have the odd function, then we will get. So, here it is a odd function. So, if we have odd function, we will get only the sine terms in the expansion. So, now what we are going to discuss here, the half range Fourier series. The idea is exactly what we have discussed for the odd and the even functions. So, let me just explain here. Suppose that f x is a function defined only in the interval 0 to this big L, and suppose we want to express this f x in the cosine or sine series. Now, here we are putting our choice that we want to express this f x function, which is defined in some interval, into a sine or a cosine series. In the earlier lecture, for instance, we have seen the Fourier series, and naturally when the function was odd function, it was coming sine series. When the function was even function, it was automatically coming as cosine series. But now the situation is different. So, the function is again defined in some interval. We have basically a choice of getting the Fourier series, which will have sine and cosine both the terms. But here the aim is not to have the Fourier series, but aim is to have either Fourier sine series or cosine series, meaning the series which has only sine terms or cosine terms. So, how to do that? So, this can be done by extending this f x to an even or an odd function, and this is exactly the idea which will be used now from the previous lecture, that once we have a function which is an even function, then its Fourier series will have only cosine terms, and when we have an odd function, then its series will have only the sine terms. So, if we want to express f x in a sine series, so the objective is to express this f x in cosine series, then we will extend naturally this f x as an even function in the whole interval minus L to L. So, 0 to L the function was already defined, and we will now define in the interval minus L to 0. So, that the whole function in the interval minus L to L becomes an even function, and once we have the even function, so naturally we will have only the cosine series of that new function. So, here we will redefine the function. Let us say the new function is h x, such that in the 0 to L we have exactly f x, and in the minus L to 0 we have minus f minus x. So, that this h x now becomes the even function, and when we write the Fourier series of this, it will have only the cosine term. So, we will get automatically a cosine series. And on the other hand, if we want to express, for example, this f x in sine series. So, if you want to express now in sine series, then we have to extend this function as an odd function in the interval minus L to 0. So, that in the whole interval minus L to L, the function becomes an odd function. So, this is the idea again, which was also explained in the previous lecture, but now we will go into more details. So, the g x is f x, this is given already in 0 to L, that the function f x is given, and in the interval minus L to 0 we have extended it as f minus x. So, that this h x becomes an odd function overall. Well, so having this now, we have this result. So, for example, f is a piecewise continuous function defined in the interval, in some interval 0 to L. The series f x with a by 2 and we have a n there and then cos n pi x over L. This series with this a n is called half range cosine series of this f, and we know now how do we get this cosine series. We have extended the function f in the range minus L to L, minus L to 0. So, that the whole function becomes an even function, and then we can write its Fourier series, which will be automatically a cosine series given here, whose a n's we can compute with this formula and b n's naturally will be 0. So, this is called half range cosine series. So, there is a difference than the chapter, then the lecture which we have discussed in the previous lecture. So, there the function was an even function or an odd function, and then we were computing its Fourier series, or we were evaluating its Fourier series, and then automatically it was coming as a sine series or cosine series. Here the situation is different. The f is given in the interval 0 to L, and we can have both the possibilities. We can extend it as a, so that the whole function in the range minus L to L becomes an odd function or an even function. Accordingly, we will get either this half range cosine series or half range this sine series, where the b n we can compute with this formula 0 to L's f x sin n pi x over L and this factor 2 over L, and this is called half range sine series. So, for a function given in some interval, we can have both the expansions, the half range cosine expansion or half range sine expansion. On the other hand, for a function given defined in 0 to L, we can also have its Fourier series, which may have both the terms sine and cosine. So, to get only the cosine terms, we have to extend the function to have an even extension or to have an odd extension, so that we get only the cosine or the sine series. So, just a short remark, note that we develop a Fourier series of a function f defined in the interval. So, we can develop the Fourier series, not the half range, the Fourier series, and it will in general contain all sine and cosine terms, and this series if converges, we know that it will represent a L periodic function, because the function was defined in this 0 to L region. So, suppose this is the function in 0 to L, and when we write its Fourier series, then it will have just an that series will converge to such a function, which is a periodic with period this 0 to L. But now, the idea of this half range series is entirely different from the Fourier series which we have discussed so far. So, here we extend the function as per our desire to have sine or the cosine series, and the half range series of the function f will represent a 2 pi periodic function. So, for instance, if I consider the same function defined in this 0 to L, and suppose I want to have a sine series of this function. So, what I will do, I will make an extension to this function in this region minus L to 0. So, that the function in this range minus L to 0 now becomes an odd function, and now I can write down its Fourier series, and that Fourier series will converge to a function which will be 2L periodic, not just the L periodic. So, I think the idea is clear with this remark. So, we can proceed further. We want to obtain, for instance, the half range sine series. So, here the objective is to have the sine series. We could also get the cosine series. So, but let us go with the sine series first. So, exponential function e power x given in this region 0 to 1, and we want to write its sine series. That means, we have to extend this function in the interval -1 to 0, so that the whole function -1 to 1 it becomes as an odd function. So, if this is for example, this exponential function x in the interval 0 to this 1. So, what we do, we want to have this extension here. So, this was the given function, the exponential function in 0 to 1. What we have done, we have extended this, so that the function in this range -1 to this 1, it has become now an odd function, and now we will write its Fourier series. So, if we write the Fourier series of this function, then naturally this will have only the sine series, and we have the direct formula now. We do not have to write the Fourier series of this function. We have already in the previous slide, we have discussed that what is exactly the formula to compute sine series when the function is given in some interval 0 to L. So, we can compute its half range sine series. So, for half range sine series, we have to compute this B n, the Fourier coefficients B n 2 over L and 0 to L f x sin n pi x over L. So, the L is 1 there. So, we have 0 to 1 the function e power x, and then we have sin n pi x, and the L is 1 again. So, this we can integrate by parts. So, we have e power x sin n pi x 0 to 1, and then this sine has become this cosine, and e power x will remain again e power x when integrated. So, this n pi factor has come now, and then we can simplify this. So, we can in this case, for instance, here the sin 0 will become 0 and sin n pi will be also 0. So, this term will become 0, and the second term again we have to integrate, and we will get this result here, which can be simplified to get in terms of this b n again, and if we take this to the other side, and we can simplify for b n. So, after simplification, we are getting this b n as 2 n pi 1 minus e minus 1 power n and 1 plus n square pi square. So, having this Fourier coefficients now, what we can do, we can write down the sine series, because here the objective was to have sine series. So, the sine series for e power x will be this 2 pi, this 2 pi there, and then the b n, this coefficient is substituted here, and then we have this sin n x term, and this equality here we have written this equality, which is true in this region 0 to 1, because we have the continuous function. So, our function was this e power x in this region 0 to 1. So, this function is continuous in this range, and naturally by this Dirichlet's theorem, this Fourier series will converge in this region 0 to 1. We will have a problem at 0, we cannot make this equality at 0, because it is an odd extension, and at 0 at one end the value is 1, the other end it is minus 1, and we have to take the average. So, it will become 0. The Fourier series of this whole function with the extended portion will converge to the 0 to 0 at 0 only. So, that is but in 0 to 1 we can certainly write this equality. So, this Fourier this series here is equal to e power x, and it has only the sine term. So, this is the sine series. Just to plot this, so this is the sine series we have just evaluated, constructed. So, this was the function, this was our function E x, and you remember this the extension was done such that as a whole from -1 to 1 the function becomes the odd function. And now, if we plot this sine series for the whole range of R, so we will have this structure again, this one, and it will converge to something like this. So, here again here and this one and so on. So, that will be the Fourier series, and in this middle this will go to, will always pass to 0. So, at the point of this discontinuity it will converge to the average value, otherwise it will converge to for any other value of x to exactly this exponential function. So, what is interesting now, that if instead of this sine series we could have obtained for the same function e power x as a cosine series. So, we can have the other representation of e power x in terms of cosine functions. And what is interesting, that in this region 0 to 1, so that in terms of the cosine will have a completely different convergent function, but in the region 0 to 1 it will again match with the e power x. So, we can have two different expansions here, one is purely in terms of sine, other we can obtain the cosine series in terms of cosine, but both the series will converge in this 0 to 1 to the same function e power x. So, we have also for instance plotted here the cosine series. So, if we write down its cosine series with the similar steps, we have to follow what we have done before. So, in the region 0 to 1, this will be equal to this exponential function, which was extended now this time. So, that it has become the even function in the interval 0 to 1, and then we have written the Fourier series, which is now the cosine series, and so the same function here in this region e power x, and now it is represented by the pure cosine terms, but it is also converging to the same exponential function. So, we have e power x completely in terms of the cosine. In the earlier slide, in the previous slide, we have e power x equal, it was written in purely sine terms. Well, so we can proceed now to another example. Here we will consider f x as sine pi x over L in the interval 0 to L, and we will write down its cosine series in this range 0 to L. So, again the similar steps. So, for the cosine series we have to compute this a n, which is 2 over L and 0 to L, and with the sine pi x and then cosine n pi x over L. So, we can use this 2 sin a cos b formula, and then we have to integrate it. So, I believe this we can proceed further. So, with the sine we have the cosine term, here also we have cosine term, and then so this was the integral, and then we have to put the limits 0 to L. So, which comes out to be such an expression, which can be again simplified to get these values of a. So, a n will be 0 when n is odd, and when n is even, this is simplified by 4 over minus this pi and n plus 1 and n minus 1. So, we have this a n, and then we have to also compute this a 1, because this was the n equal to 1 was excluded in the computation, otherwise we cannot have this n minus 1 in the denominator. So, this a 1 we can calculate separately. So, that is the result for the a 1 when we put n equal to 1 there, and that can be again integrated, and what we realize that the a 1 is 0 in this case. So, the Fourier cosine series of this f is given as then in terms of the cosine functions, which is valid again in the region 0 to L, and we have equality because of the continuity of this sine function in the interval 0 to L. So, what is interesting here, that this sine function sine pi x over L is written in terms of purely the cosine functions. So, that is how we given a function in a range. Now, if we want to compute the Fourier sine series, we have to just extend this function as an odd extension, or if you want to have purely cosine terms, we have to extend this as an odd even function. So, here the sine function is written in terms of the cosine functions. Well, so just to look at again what is happening here for the cosine series of this sine pi x over L. So, we had this function here sine pi x over L in the interval 0 to this L equal to 1 we have taken here. So, 0 to 1, and then we have written this cosine series making this extension as the even extension, and then as a result this Fourier series is having these cosine terms, and we got the result which was just given in the previous slide. Well, so now here we want to expand, for instance, this f x is equal to x given or defined in this 0 to 2 in a sine series and as well as in the cosine series. So, we can do so because we have to just extend this function in the interval minus 2 to 0 accordingly to have sine series or cosine series. So, to get this sine series we need to compute just b n. Indeed, we do not have to extend it, I mean we, but the idea should be clear that what is happening here, but with the help of already discussed these formulas, we will just compute b n and write down its sine series. For the cosine one, we will just have the a n's and then we can write down its Fourier series. So, we do not have to basically expand it, extend the function as an odd extension or even extension, and then we have to write the Fourier series. That is not needed. So, we will just now compute this b n. So, b n is 2 over L and then 0 to L f x sine n pi x over L, the general formula to compute this b n. So, here L is 2 and then we have 0 to 2 x sine n pi x over 2. So, which we have to integrate by parts. So, the first is x as it is, then we have the cos for the sine, and then just to have this integration we have to also have minus sign there, because sine is integrated, and then we have cosine with the minus sign, and this 2 over n pi factor will be appearing there. So, again the same thing there, 2 over n pi factor with the minus sign, and minus was there. So, it is adjusted, and then we have the differentiation of this x which is 1 here, and then the again we are getting this cos n pi x over L. So, which can be further integrated. So, first here also we will have, when we substitute this 2 there, we will have cos n pi with this 2 there, and then 0 we will have 0 there. So, all we have to simplify this to get this minus 4 over n pi, and then we will have this cos n pi term. So, in this region 0 to 2 we can have this Fourier sine series, because we have the b n's ready now. So, the x can be written in terms of the sine series now with the coefficient here 4 over n pi and this cos n pi, or we can expand it. So, we are getting these only the sine terms in the series, and this is the representation of this x. We have the equality there. So, in the interval this 0 to 2 we have this equality. So, this series will converge, because we know this result from the Dirichlet theorem, that at the points where it is continuous it will be equal to exactly the function was x there. So, we have the x equal to this series which is having purely sine terms. Well, we can also express this f x is equal to x in the cosine series, and for that we need to calculate now a n's for n not equal to 0. For a 0 we will do this separate calculation. So, here we have a n again with the same formula 2 over L 0 to L, we have this x cos n pi x over L, and we can integrate this by parts again. So, x, and then we will get sine there, and again sine, and the differentiation of x will be 1, and then we have to differentiate again, because this will become 0, and but there we have to differentiate to get this cos term and the limits from 0 to 2 again. After substituting this limit 4 over n square pi square, we are getting cos n pi and this minus 1. So, we have the coefficient here for a n as well. So, we can write down it's a series here with this n. So, the coefficient a 0, right, we have to compute separately because this was not possible directly with the a n because of this denominator n. So, a 0 we can separately compute, which is coming 2 there, and now we can write down the Fourier series for x, which is x is given in the interval 0 to 2. So, we have x equal to completely the cosine series. So, the same x, the same function which was given in the region 0 to 2, at once we have purely the cosine series, and now the earlier one we had just the sine series representation of this cos x or for this x, and now we have written this x with the equality sign, in the region this 0 to 2 we have written now in terms of the cosine. So, that is the beauty of this half range sine or cosine series, that the given function we can write down either in the sine series or in the cosine series. Well, just to see that what is happening here. So, this was the function given in 0 to 2. So, in 0 to 2, and then the Fourier series will converge to a periodic function with period 4, because this is the extension which has to be done there, though we have not explicitly done there and got the Fourier series, we have applied the directly formula, but we should know that what is exactly happening. So, the one period of this function is going to be from this minus 2 to 2, and this was an odd extension of this function. So, naturally we will get the sine series in this case. For the cosine series for this f x function, we have so this is the function given x in the interval 0 to 2, and now we have to have this odd extension and even extension, and then the Fourier series will converge to exactly this one here. This will be the period now which will be repeated here to have this periodic function. So, the Fourier series now it is converging to this function in the case of cosine series, in the case of sine series it is converging to this function. So, for the cosine case, for instance, you have the continuity everywhere, and so the value of this Fourier series, the Fourier cosine series will be exactly the value of this function at any point, but in this case, for example, we have the problem at these points there, but then it will converge the Fourier series to the middle one. So, to the 0 to the average value. So, that we have already discussed with this convergence results earlier. Well, so these are the references we have used for preparing these lectures, and now to conclude that what we have discussed in this lecture, suppose this f is a piecewise continuous function which is defined in the interval 0 to L, then it is our wish to write down the cosine series, or we call it half range cosine series, where the f x can be represented by purely in terms of the cosine functions, where the a n is given by 2 over L and 0 to L f x cos n pi x over L. Or if we wish to expand this in the sine series, then we have to compute this b n with this 2 over L 0 to L f x and sine n pi x over L, and then we have the pure sine expansion of the function. So, there are 3 possibilities now, at least 3 possibilities we have discussed. Given a function in the range 0 to L, we can construct its Fourier series, which in general will have sine and cosine both the terms, and the Fourier series it will converge to L periodic function, and exactly this period will be defined by the given function 0 to L, because we have written its Fourier series. Now, for the half range series, so if we want to have this cosine series, then the cosine series will converge to the periodic function having period 2L, because now in one period the function will be defined from minus L to L, and minus L to 0 it will have just even extension, then only we will get this half range cosine series. Similarly, for the half range sine series, the Fourier series, this half range Fourier sine series will converge to the function having period 2L, and in one period will be defined from minus L to L, and from minus L to 0 we will have the odd extension of the function which is defined in this 0 to L. So, I hope this is the idea is clear of the half range, which is entirely different from the Fourier series. This is based on this odd and even extension, and to have the desired Fourier series either in terms of sine functions or in terms of cosine functions. Well, so that is all for this lecture, and I thank you for your attention.